Well, hello, ap2. We're starting up chapter 11. This should be video part 1. And this is going to be a test of my new fancy, not just any kind, but my new fancy pen or stylus. I got one of those Apple pens, it looks like, so we'll see if this is any good. Chapter 11, let's go look at the book. Chapter 11, Energy and Thermal Processes, page 352. So, first thing we want to talk about is something we've talked about before, heat and internal energy. Oh, by the way, students of past years have said that I look a little bit like James Jewell. Kinda. Losing hair. Gray beard, awesome looking beard. Anyways, there's Jewel. So the first thing I want to talk about is internal energy. We've discussed this before. We said that the kinetic energy of all the particles that make up some sort of material, like a gas, for example, we said that the kinetic energy of all the particles was called the internal energy, and we said it was internal because we were describing the energy of something in a microscopic sense, at an atomic sense, not the macroscopic motion. So, you know, my iPad right now is just sitting here not doing anything, but that doesn't mean that it doesn't have internal energy. The atoms that make it up are still moving around like crazy, so there's a lot of kinetic energy there. Internal energy. Heat is the transfer of energy between two systems due to a difference in temperature. So remember we talked about the hot air in the classroom and the cold air in the hallway. We put them in thermal contact, and literally via collisions, kinetic energy is exchanged between the hot, high energy thing and the cold, low energy thing. Well, that energy that's being exchanged via those collisions is called heat. So we have, oh, by the way, with my fancy pen, I can push my finger on the screen and my finger doesn't write because only my pen writes. That makes scrolling kind of slick. So anyways, internal energy. The internal energy. We're going to use the symbol U for internal energy. And heat, we will use the symbol Q. So obviously, internal energy is U and heat is Q. So that's, well, obvious. And both of them are forms of energy. So both of them will have the units of the joule. So both will be in units of joules. So internal energy is still energy, heat is still energy, the units are still joules. A couple other energy units that you might be familiar with that come up thermodynamically, although these aren't our preferred units, it's the energy of the calorie. 1 calorie, you know what calories are, you've eaten food before. 1 calorie is defined as 4.186 joules. Now, I find this next part really funny. Some of you probably won't find this funny. But this calorie here, that is not the calorie we use to measure our food. We actually measure food in something called a kilocalorie. And a kilocalorie is defined as 4,186 joules. It is the kilocalorie in the United States that we call calories. So, when you buy a Snickers bar that is 200 calories, what you're actually talking about is not this kind. You're actually talking about this kind. So in terms of calories, your Snickers bar is actually, gulp, 200,000 calories. And that makes me laugh. Not that it matters, because I mean 200,000 and 200, it's just this different units, but still it makes me laugh to think about 200,000 calorie candy bar. Anyways. Alright, so if we go to the next page, page 355 for the next topic, we're going to talk about something called specific heat. Now, your book gives an equation, and I'm going to go to it now. Your book, by the way, we can look at this problem in class. Your book gives this equation for specific heat, 11.2, and it also mentions equation 11.3. So both of these here, and well, I'm actually going to backtrack a little bit because I think This isn't exactly fair to say it this way, I'll be honest. There's actually something important being left out here, and the thing they're leaving out is going to come back later anyway. So I'm going to describe heat and specific heat slightly differently than the book here. I just don't think it's quite fair what they're saying. And you'll see that once I'm done that we'll come back, we'll end up in the same place, but they did something that's not, they just left something out that they shouldn't have. So we know from before that the specific heat of something can be written as 3/2 capital NKT, or we had 3/2. The other one we had was 3/2 nRT if we wanted to do it that way. Well, that's basically just a series of constants and the temperature. Well, you can write the internal energy, and we're not going to derive this right now. We can come up with this some other time, but for right now, take it on faith. Different set of units, MCT. So a change in internal energy would be written as MC delta T. Okay? And C here is called the specific heat. C is called the specific heat. The specific heat is a materials dependent constant. So if I add heat, and the way you add heat is basically like we described in that hot air, cold air, classroom air, hallway air, and our little kinetic energy collisions. If I exchange heat energy, the internal energy of both objects in that process will change. The internal energy of one object will go down, and the internal energy of the other object will go up. The hot one cools down, the cool one gets hot. Well, when we say that, that means the temperature changes, and we've already described this. Now, the specific heat has to do with the way a material responds to having its internal energy changed. So, an object with a very large specific heat will absorb a large amount of energy before its temperature changes very much. An object with a small specific heat will absorb a large amount of energy and will experience a large temperature change. So if we go to our book to table 11.1 on page 355, you will see, for example, that water has a specific heat at the bottom of this table of 4,186. 4,186 is a huge number. Gold, you will see, has a specific heat of 129. So if I put 10 joules of energy into water and 10 joules of energy into gold, they will not experience the exact same change in temperature. Okay? So materials dependent. Next, the way that I can change the specific heat, the way I can change, not the specific heat, sorry, brain fart, the way I can change the internal energy of something. By the way, this equation quite often gets written as U equals MC delta T. We always think that change equals change, but it's very common that we don't bother writing that symbol. So if you see it like this, don't freak. The way that we change the internal energy of something is by adding or subtracting heat, and doing work. So I can add or subtract heat, and that would be putting two things in thermal contact, like the hot air and the cold air in the classroom. The other way is I can literally do work on an object. Okay, I can do work on an object, in which case I'm applying forces through some displacement, energy is being dumped into that object. I can have the object do work, in which case the object is losing energy by doing work. Either way, that changes the internal energy. The internal energy, we said, could be written as MC delta T, so that has to equal Q plus W. Which means the equation the book gave for heat is assuming that there is no work being done. If no work is being done, then the amount of heat is in fact MC delta T. But to say that heat is MC delta T, I think is disingenuous. I mean, it has to be under the assumption that no work is being done. So that's why I decided to go back and try to explain this concept a little bit. So at any rate, I hope that makes a little bit of sense. We now have heat, we have internal energy, and that should allow us to do one or two problems out of the textbook, which is what we will do once you're done watching this video. So for now, let's just call it here.